Thanks everyone for staying. It's already late afternoon, so I will try to make the talk less technical than it was supposed to be. Following Ronit will be a bit difficult, but okay. Okay, so PCPs, one way to think of them is a robust proof format that allows probabilistic checking. Another way is to think of them as a hardness of approximation reduction, transforming any three-set instance to a gap three-set instance. And the third way is like an encoding, like an error-correcting code. So let's think of a PCP as an algorithm that is like an error-correcting code. So an error-correcting code is an algorithm that takes k bits and outputs n bits. See, these are my bits here, and then they are moved to n bits. And this transformation introduces robustness, so you can recover even if there's some errors. And a PCP encoding, if you will, or an algorithm, takes a couple of things. It takes a string x, or you just think of the string x as a solution to an equation system E. So really, your input is a bunch of equations over n variables. And the PCP algorithm converts them to another system of equations over new variables. So it doesn't only encode the bits, it also encodes the equations. It encodes two levels of objects. And this encoding has a bunch of properties. I won't kind of formally get into it, but basically, you want to introduce robustness both to the encoding of the bits, but also to the encoding of the equations. In particular, when you think of the solution space of these equations and the solution space of these equations, they're related. For example, if there's no solution, there won't be any solution. But also, if you have a solution here that's not a really good solution, it's only an approximate solution, still the PCP transformation guarantees that this means that there exists an actual solution to the original instance. So that's kind of introducing robustness on two levels. Okay, and the talk is about PCPs and high-dimensional expanders. So my goal in the first part of the talk is to show you an important component in the construction of PCP, which is called an agreement test or a consistency test. And then I will show how this is, in some sense, a high-dimensional expander and talk about high-dimensional expanders. I don't assume that you necessarily have heard about this before. So we'll see. OK, so how do you construct this PCP encoding? You need to encode two things simultaneously. You need to encode the bits of the solution. Remember the variables x1 to xn. And you also need to encode the equations, or sometimes we call them the constraints. So you encode both the bits and the constraints. OK, so I mean, the color is surprising. OK, so can you read that over there? No, it says agreement. Sorry. OK, so how do you do that? Well, one thing I need to tell you is, actually, you can do it quite easily if you don't need to be efficient. If you can allow yourself all possible functions over the input, like the long code, then this is actually a relatively straightforward task. The encoding is just look at all possible functions over the inputs and do some folding. But if you want to be efficient, this is no longer easy. And the solution that we know is to break the instance into small pieces and kind of recurse on each piece. And the point is that the pieces want to be overlapping, because otherwise this won't work. You want to check consistency between the different pieces. So that's important. And let's see a picture. Yeah. So here is the big global picture. It's like this whole globe. And this is like the proof that I want to encode. And I don't know how to do it, so I break it up into small pieces. So these are these little patches. And I imagine that on each patch, I can afford to run some maybe less efficient PCP. And so, the prover writes down the proof, and this is the proof the prover wrote for this patch. And this is the proof that the prover wrote for this patch. and so on. And now I want to do some local check. And the local check is that two patches that have some overlap kind of meet, and they compare nodes, and they see if they agree or not. Okay, so this is a picture of a generic agreement test situation. Okay, and the question is, I want to talk about this kind of at length, but first let me show you that if you've heard about PCPs and you know some PCP constructions, you have seen such things before. So let me give you some examples of these objects that exist in the PCPs we know. Okay, so first is the low degree test, say the line versus point low degree test, or many different variants. So what is the situation? So we have some vector space f to the d, and we have the variables. Remember x1, x2, x3, x4, x5, x6, all the way up to xn. We put them in a box, and then we do this low degree extension where we put them in kind of a box that's inside this f to the d. And then we think about this low degree polynomial that whose values on these points is supposed to be the solution, but the polynomial also has values all over the place. And then we look at lines through this space. Okay, so all possible lines through this space. We also look at curves through the space that maybe pass through some of the points, so that when you ask the prover to give you a function on the curve, you also are going to check that this function satisfies some constraints that are supposed to be satisfied on these points. Maybe there's also a hidden sum check procedure that I'm hiding here. But anyway, the point is, you take your original proof, you do some non-trivial manipulations to it, and then you encode it through a low degree function. But then you break up this function into pieces, into these lines and these curves. Okay, and what you ask the prover, for every line, you want to get what is supposed to be the restriction of this global proof to this line. Okay, so what you've done is you've broken this global polynomial on f to the d into many, many pieces, these lines. I'm sorry about the colors. You've broken them into many, many pieces. Each line is a different piece. Maybe you also have pieces for curves. Maybe you also have pieces for two-dimensional objects like planes. There are many different variants here. But the point is that now a key component is to check like a line versus line test. You look at pairs of lines that intersect, and you check that the function that you got on this line is consistent with the function that you got on the other line. And that's an agreement test. You check that these two lines agree. So that's, you see how this is an example of this picture with the globe, hopefully? Okay, good. Good. So that's a line versus line test. Here's another totally different example. This is the gap amplification proof, the combinatorial way to prove the PCP theorem. So you have some graph. Okay, this is just part of the graph. The vertices of this graph are our variables, and the edges of this graph are the equations. So this was our original instance. You had variables, you had equations. So an equation can really be not only over two variables, it can be over 15 variables maybe, but it's good to think of it as a two-variable equation, and it's okay. So you can easily reduce between those cases. So you have your graph, and now you want to encode it somehow. And the gap amplification step says, okay, I'm going to look at balls in this graph. So first of all, I'm going to make sure this graph has some expansion. That's easy to do. Suppose that the graph is already an expander. Then for this vertex, look at all of its neighbors. Maybe not only neighbors at one step away, maybe 15 steps away. So it's some neighborhoods of some radius. And this is going to be one piece. And this is going to be another piece. And this is going to be another piece. For every ball in this graph, you're going to have a different piece. And what you're going to ask the prover is to give you, for each piece, an assignment to the variables in that piece. And this assignment, you're going to check that it satisfies all of the equations that are inside the piece. So you know that locally all the constraints are going to be satisfied for each piece separately. But then the agreement test is going to ask whether two pieces that have some significant overlap actually agree on the bits that are in the intersection. And what you prove when you prove the gap amplification step is that if you have not 100% agreement, even just 1 minus epsilon agreement, then this implies something non-trivial. You can deduce from it an assignment for the a global assignment for the graph that has even better satisfiability than you had before. So, of course, we're not doing any details here. My point is that we want to look at a global assignment for the vertices of the graph, and instead we look at pieces, so local functions, each one assign just a piece of the graph. And we do this agreement test where we say, if the pieces agree when they overlap, then I can deduce something global. Okay. Okay, here's another example, label cover. So how do you prove hardness of label cover? I don't remember if we've seen what label cover is or not in the morning guide. Did you show it? Dol, did you show it? Okay, so you know how we said that the PCP theorem is like a gap, it's hardness for gap 3 set. So label cover is like a gap 3 set instance where the gap is very large. It's between almost 0 to 1. So in the good case, everything is satisfiable, all the equations. And in the bad case, only epsilon fraction are satisfied. It doesn't matter exactly. That's all that I care about here. And so how do you do that? Suppose you already proved the PCP theorem and you have a kind of an instance here that has a gap. So you know that it's NP hard to decide if all of the equations are satisfiable or if at most 99%. So what we do is kind of a parallel repetition step. Also, you can think of it as direct product. And in this parallel repetition, you put all your variables as points in some space. This is how I interpret this drawing. Every point here is a variable. And there's also edges that represent the equations. And now I look at a k-tuple of equations. So I choose k, say, edges here. And I look at all the variables. So maybe it's 2k variables. And that's one blue subset. That's one piece. I look at another k-tuple of edges, and that's another blue piece, and so on. And actually, sometimes there's different variants here. Sometimes you even, see here I wrote, sometimes you look at a set of variables coming from k equations. And sometimes you look at a set of variables, of k variables, that you choose k variables. So it's different kinds of pieces. And what you require is that on each piece, you're going to get an assignment to those variables that needs to satisfy all of the constraints within that piece. So if there were no constraints, then you can do whatever you want. If there are some edges, the assignment should satisfy the constraints on those edges. And this is what the pieces, the local pieces are. And now the agreement test is to check that two overlapping pieces actually have the same value on the common variables. Okay, and to prove that this is indeed, if you have local agreement, it implies global agreement. This is done by the parallel repetition theorem or a bunch of different direct product theorems. There's many different variants to this question and many different papers about this. Any questions, by the way? Okay. Okay. So here's another example. It's actually an example we've seen a couple of slides ago and also in Dol's talk. So here again we have some vector space f to the d. And here I'm looking at two different subspaces, L1 and L2. Previously we looked at, say, two lines. So that was a one-dimensional or affine subspace. And now I'm looking at maybe a higher dimensional subspace, an L-dimensional subspace. And compare two subspaces if they intersect. So again, you're envisioning that the proof is some global function. For example, in Dol's talk, this global function was a linear function over all of f to the d. And you're requiring the prover to give you a linear function on every subspace. It's supposed to be the restriction of the global linear function to your subspace, but the prover can do something else if they want. And what the agreement test is testing is that if you have two subspaces that have high overlap, you want the linear function to totally agree in the intersection. And again, it's important to understand that these agreement testing questions have quite different flavors. Here, for example, we really care about agreement testing in the low soundness regime. So we say, suppose you know that the prover gave you some bunch of local functions here, and suppose you know that they satisfy the agreement test only with probability 0.1%. Even in this case, you want to deduce some global behavior. And we know that you can't expect to find a global function with which everyone agrees, not even a global function with which 0.001 agree. But there is some structure nevertheless, and that's good. Notice also that when the subspaces have very high overlap, you get the agreement test is indeed a 2 to 2. I'm not going into it, assuming you've seen this in Dole's talk. If the subspaces have less of an overlap, then the test is no longer 2 to 2. Maybe it has better soundness properties. So there's different variants of these questions, but they all kind of, in some sense, look at the same underlying geometrical structure. Okay, and you've seen so we've seen 4 examples: the low degree test, the gap amplification, label cover, and the Grassmann from the 2 to 2. These are different kind of components in different PCP constructions, but in all of them you have this agreement test where you break a global function into local pieces and you use the overlap in the test to kind of move from the local to the global. That's kind of a central component, I would say. Okay, so it's natural to ask this. In what situation do you have an agreement test? Of course, this is not well defined in agreement test. There's many parameters and many flavors, but just let's be vague for this talk. So this is a very natural question to ask. And it was asked it was asked before me many years ago. So what are we talking about? So there's a ground set V of points or vertices, if you will. And then you have some family of subsets, like the points in a line or the neighborhoods of a vertex in an expander. So each subset is some set of points of V. And you have some test distribution that says, S1 and S2 belong to this family of subsets, and you're going to choose a pair of them according to some distribution that is specified by the test. And what you want to prove is that if for every subset you have some local function, and if the test is always going to be a consistency test. So it's always going to look at 2 local functions and ask whether or not they agree on their intersection. What you want to prove is that if the test succeeds with high probability, this can only be explained by a global function. So what do you need for this to work? For sure, you... That's true. So what Boaz is saying is that actually, for example, in the Grassmann situation, we didn't allow every subset, which was an L-dimensional subspace, to have some arbitrary function on it. It had to be a linear function. And this was very important for the analysis. So I hid this here. I didn't get into it, but definitely that's another parameter. Okay, so what do you need for sure? Definitely you need non-trivial intersections between the subsets. For example, think of this kind of first example that you can think of is a bunch of n points, and you take random subsets of, say, k elements. If k is small and you take a linear in n number of subsets, the intersection will typically be either, well, 2 sets usually will be disjoint, and at most they will have intersection of 1 point. And this is kind of not strong enough intersection. Somehow none of these things will work this way. So that's one thing you want, non-trivial intersections. And the other thing is that you want some kind of expansion. And this we've seen maybe in Dole's talk, the graph that you can look at the collection of pairs S1, S2 as if it's a graph. The points are all the sets now. And you connect a pair of sets if there's a test between them. It's clear that if this graph has a lot of small components that kind of barely have outgoing edges, then you can construct counterexamples. You can have a different global function, pseudo-global, for every little piece, so it won't be good. Okay, so this is definitely something you need, but this is far from sufficient. And people have looked at this question and tried to come up with sufficient conditions where for this to work. So the first people who actually looked at this question abstractly was in a paper of Goldreich and Safra. They were looking at the low degree tests that I showed you in the beginning and said, well, what's so special about low degree tests? There's an underlying, a more abstract question. Let's try to find a combinatorial version of this low degree test, and they succeeded to do so. And then later, direct product testing were studied, and in a paper of IKW, they tried to give some kind of a collection of axioms or properties that will make this test succeed. Also, in work with Or-Meir, we tried to do it, but if you look at these lists of axioms, they're very long and kind of. When you abstract something, what do you want? You want to gain something new, some new knowledge. Like, you don't want the abstraction to be more complicated than the only two instances that you know. So somehow this got stuck, and really we only knew two examples. One example is the collection of subspaces, and the other example is the collection of all possible k-sets. This is like the direct product example. So that was that. And then this leads me to this relatively new topic. So I learned about this, I want to say 3 years ago, but really it was longer. So this new topic of high-dimensional expanders, which is another way to understand many different scenarios where an agreement test works. At least this is how I want to present it in this PCP talk. So I've heard about high-dimensional expanders maybe longer ago than this, maybe 6 years ago, but somehow I didn't understand what it was, and I didn't realize that it's connected to PCPs. And then 3 years ago, Tali ran a seminar at Weizmann with Joseph Bernstein, and they kind of described these things from various directions, and suddenly kind of they managed to explain it in a way that it became clear that you have a collection of subsets that have non-trivial intersections. And that somehow seemed very compelling. So I started to look at these objects more carefully. So what am I going to talk about for the remaining, for my remaining time in this talk? I want to explain what a high-dimensional expander is, and I'm going to use a new definition based on random walk. So I mean, I don't really expect most of you to have seen the whole definition, but there's many definitions floating around, and not all of them are equivalent to each other. This definition, I think it's nice because it doesn't, because it kind of contains within it both the Grassmann case and the hypergraph case. So that's why I want to present it now. So that's what I'm going to do first. I'm going to show this definition on hypergraphs, or better to be viewed as simplicial complex. I'll say what this is. But then we'll generalize them to partially ordered sets. So it's a bit more general, and this includes also the Grassmann case. So we'll do this. This is going to be the definition. And then I'm going to show briefly what you can do with this definition. For example, you can do Fourier analysis. So like we have functions over the Boolean hypercube. You can decompose them into Fourier levels. You can also do functions over the high-dimensional expander and decompose them according to levels. And this is a nice, nice thing. And also, as was conjectured and later proven, we can actually prove that a high-dimensional expander does support agreement tests. So this is first we proved it with Tali for these Ramanujan complexes, and then some further work with Yotam Dickstein. Just to remark that something very kind of surprising happens. The fact that these hypergraphs that are high-dimensional expanders even exist is very non-trivial. It's quite amazing, and it's based on, we have some algebraic constructions to show it. There is no kind of random construction, for example, just like you don't have any random constructions for PCPs. in this definition, we also it's not only a definition that works for hypergraphs, it also works for example, for collection of subspaces. So you can ask whether an analogous bounded degree Grassmannian object exists, and this is something I might talk about at the end of my talk, depending if I have enough time or not. Actually, is there a clock so I know what time it is? Thank you. Oy vey voy. Aha. Muli, can you see this? Okay. All right. So here, what do we have in this picture? We have 6 vertices, purple, and 3 hyperedges. Each one of them contains 3 vertices. Okay. So it's a 3 uniform hypergraph. Now I want to first address the question of why are you saying high dimensional? What is high dimensional here? Okay, so the high dimensional is that instead of a graph where you have vertices and edges, you also have higher dimensional hyperedges. Like here, they have 3 vertices in them. Okay, so that's what is high dimensional. And of course, we're going to look at hyperedges that are larger than 3, going larger. And instead of really just looking at a graph, we're going to look at a hypergraph, sorry. You're going to look at a simplicial complex, which is a hypergraph where you also include all the subsets. So you also include the edges in this case. So you see, I had here a 3 uniform hyperedge, and I added this edge, and this edge. So it's always going to be downwards closed. So that's a simplicial complex. And when you talk about this object being an expander, you're going to talk about expansion in all the different layers. So this is something I want to explain much more slowly now. What does it mean to be an expander? Ooh, wow, this is going from dechi to dechi. Okay. I'm really sorry about this. So I didn't test out these slides before, and now I regret it. So look, this is really an important step in my talk. So here is a simplicial complex. Okay, you have vertices, edges, and triangles, and here is a less compact representation of the same object. So what do I have here? I put the vertices in the bottom layer, so you can't even see this. Oh, no, it doesn't even exist. So I was, maybe in the next slide, I labeled all the vertices with letters, A, B, C, D, E, F, G, and E, F, I guess. And here are the vertices, OK? So A, B, C, D, E, F, 6 vertices. And then all the edges. So there's a triangle between vertices A, B, and C. So you have an edge AB, an edge AC, and an edge BC. So I'm really putting here a vertex for every subset of size 2. So here I have vertices for the sets of size 1. Here I have a vertex for the sets of size 2. And over there I have a vertex for the sets of size 3. So you see I have 3 triangles. I have 1, 2, 3, 4, 5, 6, 7, 8 edges. And I have 6 vertices. And now I have these green incidence edges. This edge, I only put it if this vertex, this subset is contained in this subset. So this is the edge EF. It is connected to the vertex E and to the vertex F. Okay, so this is a less compact representation of this simplicial complex. And you see it's a multi-layered graph, and it's kind of ranked. So here are the sets of size 1, 2, 3. Okay. So now I want to talk about expansion. And to talk about expansion, I'm going to talk about random walks on this object. So when you talk about random walk in a graph, it's pretty evident you're going to move from vertex to vertex through an edge. When you talk about a random walk of a simplicial complex, you need to first decide random walk on which dimension of faces. For example, I can move from vertex to another vertex. I can move from an edge to another edge. So I can move on different layers. And this is well reflected in this description. I can either move from vertex to an edge to a vertex, or I can move maybe from an edge to a triangle to another edge. So I can do different kinds of random walks. OK. admit. Okay. Well, just it's challenging for us. Yeah, yeah. For this talk, we're always going to consider walks that move just on one dimension. So if you start with a vertex, you're going to end up at a vertex. So see here, I have two different kinds of walks. One is the up-down walk, where you start with a subset, you go to a random set that contains it, and then you go back down to another random set that is contained in that one. Okay, so that's the up-down random walk, and it's also called sometimes the upper random walk. And there's another random walk, which is the, do you see this? Down-up random walk. So where you start at some set, you go down, and then you go back up. It's very easy. By the way, there's a convention that's very convenient here, which is to always add the empty set into your simplicial complex. So there's actually a minus one, I guess a zeroth layer here, which is the set with 0 elements, and it's contained in each one of these sets of 1 element. Okay? So in this case, you can also talk about walking on the vertices in two different ways. One way is to start from a vertex, choose a random edge that contains this vertex, and then choose another random vertex inside that edge. You might go to the neighbor, or you might go back to where you started. So actually, this kind of random walk where you start from a vertex, you choose a random edge containing that vertex, and then you choose another random vertex inside that edge. What is this? This is the lazy random walk that stays in place with probability 1/2 and goes to a neighbor with probability 1/2. Okay, so that's when you look at walk on a vertices, the up-down random walk is exactly the lazy random walk. What about the down-up random walk? So that if you're at the level of the vertices, you start from a vertex, you go down, so you go to the empty set that's not depicted here, and then you go to a random vertex that contains the empty set, which is another vertex. So this is like choosing two vertices independently. Okay, so these are two different random walks, the down-up and the up-down. Okay? And I can do them from any layer. I can also say again? I can do them in any layer except the top layer. In the top layer, I don't know how to go up. Okay. Okay. So here is the picture with the empty set over here. And I want to talk for 1 minute about these random walks, the up-down and the down-up. When we think about a graph, so in a graph I have 3 layers. I have the empty set, I have the vertices, and I have the edges. So let's think about the random walk on the vertices. Okay, so I have two versions. The first one is the up-down, where I start from a vertex, I go up to an edge, and I go back to a vertex. We said already that this is the lazy random walk. And I have the down-up. I start from a vertex, I go to the empty set, and I go back to another vertex. Should be clear that this V and that V are not the same vertex. They can be the same or they can be different. Okay, so these are two different random walks. And you know, interestingly, if this graph is a gamma expander, this is the letter gamma here. If this graph is a gamma expander, then these two random walks actually have a very interesting connection between them. So if we denote by L plus the L plus or L plus with, what are these letters? Can anyone guess? It's not, thank you, non-backtracking. So you see there's an essential difference between the up-down and the down-up in any graph. In the up-down, you have probability 1/2 of staying in place. In the down-up, you do not. So if you want to compare these two things, which I do, it's better to compare the upper walk with the non-backtracking version. So you don't allow the second step to go back to where you started. Okay, so let's do that. So this is my L plus. The upper walk that is non-backtracking, and I'm comparing it to the lower walk, okay? So what am I comparing here? This L plus NBT, this is a complicated notation to just say the adjacency operator of the graph, okay? This is just the adjacency operator of the graph. And what is this? This is just the operator that takes two independent random vertices. So it's the complete graph with self-loops. Okay, in particular, what are the eigenvectors of this thing? So you have, if suppose it's a deregular graph, you have the all ones vector, which is the uniform distribution. It has eigenvalue 1. And all the other vectors that are orthogonal to this vector are eigenvectors with eigenvalue 0. So this is like the ideal expander. And what does it mean for an adjacency matrix to be approximately equal to this operator in spectral norm? So this just denotes a spectral norm of an operator. And what this says is that the operator norm here is bounded by gamma. It means that your adjacency matrix is a good approximator to this ideal object. It's exactly equivalent to being a gamma spectral expander. Okay? So our definition for higher order random walks, meaning random walks not only on the vertices but on subsets of larger size, is just going to be a generalization of this. Oy, 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 מה קרה? Uh-oh. Shit. Okay, this is very strange. Okay, we hope that this will work. Okay, so all right, so now I have this general definition. So I have this random walk L plus, which walks from, so now I use this terminology, K face. This is just a hyperedge of size K or K plus 1. So this is just a subset of size K, more accurately K plus 1. So you walk from a K face to a K face by first going up to a K plus 1 face and then going back to a K face. And I'm looking at the non-backtracking version so that it's, I don't need to worry about the different collision probabilities. So that's my L plus. And L minus is going to be the operator that walks from K face to K face through a K minus 1 face. So it starts with a K face, moves to a K minus 1 face, and then goes back up. Okay, so these are two different operators on what? What are they operating on? They're operating on the kth level of this simplicial complex. So it's a linear operator. It takes as input a function that labels the K faces. It does something, and it outputs another function that labels the K faces. Okay? And our definition for this talk is that this hypergraph or this simplicial complex is going to be a gamma high-dimensional expander if these two operators, L plus with non-backtracking and the L minus, are actually very close to each other. They're the same up to this error of gamma. So think of gamma as a very tiny constant, okay, going to 0. Okay, some tiny gamma. Okay? And so we say that a complex is a gamma HDX if this happens for all the levels. Okay? And if you've seen, if you haven't seen other definitions before, you can just take it as our definition. If you've, yeah, this is operator norm. Yeah, it's eigenvalues. Yeah. So you can take this. If you've seen other definitions, for example, you've seen a definition that talks about the local link expansion, where you look at every set and you look at the link around it. These are actually equivalent. So this is something we proved with Yotam, Yuval Filmus, and Prahlad Harsha. And so what does this mean? It means that those beautiful algebraic constructions that give you high-dimensional expanders are actually gamma high-dimensional expanders according to this random walk definition. Spectral. All the links are expanders. Including the entire, well, I mean, you have this Garland type theorem that says that if all the links are expanders anyway, the underlying thing is an expander. This was proven by Zal Oppenheim. But yeah, so these things are equivalent. Maybe you lose some factor, like from gamma you move to maybe d times gamma. I don't remember, but okay. Okay, so before moving on, just to say, so what have we seen so far? We talked about hypergraphs and simplicial complexes. We talked about how to do random walks going down and going up. And we gave a definition of expansion that says if the lower random walk and the upper random walk are similar, in spectral norm, then you say that the thing is a high-dimensional expander. Just to be sure, if you look at an expander graph, the kind we are used to, this is usually you think of a bounded degree graph. And what I'm saying is that a definition of an expander says that this bounded degree graph is similar to the complete graph. Now, clearly, they're not similar. This one has n choose 2 edges, and this one has O of n edges. But in spectral norm, they are similar. And this is the same type of similarity we are talking about here. OK, so that was for hypergraphs that are downwards closed, namely simplicial complexes. Now I want to move a bit away from simplicial complexes. Let me make this remark. These definitions of high-dimensional expanders are kind of strange from a point of view of maybe someone who grew up in TCS, because I would never in a million years guess this definition, just because no object that I know satisfies this definition. No bounded degree object that I can build or randomly choose or something like that will ever satisfy this definition. So it wouldn't make sense to even come up with this definition. So we are lucky that these objects exist in other realms, coming from algebra and number theory. And then kind of Tali was working on these with various people, and kind of together they came up with this definition of this link expander. So when they were working on these objects, the object of study is always a simplicial complex, as far as I understand. Whereas from our point of view, when we construct PCPs, a simplicial complex is kind of a restricted family of objects, and maybe you want other things. Okay? So in this definition, maybe we try to bridge the gap between these two different domains. Okay, so this is the same picture we had before. It's a poset. What is a poset? A partially ordered set. So you think of this element as being smaller than this element, and this element is smaller than this element. And of course, you think of transitive, yeah? And what is another example of a poset? So one example is, of course, a simplicial complex. So these will be the vertices. And a vertex is smaller than an edge if it is contained in this edge. And an edge is smaller than a triangle if it is contained in this triangle, and so on. Another example will be subspaces in a vector space. So these are going to be all the points in the vector space. These are going to be all the lines in a vector space. And a line is going to be bigger than a point if it contains that point. And these are going to be all the planes in a vector space, and so on. So that's another partially ordered set. And we can look at that as well. And when we look at that, we can also look at these. I don't know if you see this, but I see something here. So you can see these random walks, the ones that you can look at the random walk that moves from a line to a point to a line, or from a line to a plane to a line. And you can compare these two random walks. So let's think about it for a minute. If I have a vector space, and I'm looking at affine spaces, so these are going to be affine lines, for example. I choose a random line, and then I choose a random point on it. And then I choose another random line going through that point. This is my walk. And another kind of walk is I choose a random line. Then I choose a random plane that contains this line. And then I choose another random line in that plane. These things look very, very similar, right? Because those two lines that are inside the plane are going to intersect exactly in one point. Almost exactly the same. There's one slight difference. And what is that? It's exactly the backtracking probability. When I choose, suppose I'm in a very high dimensional space. I choose a random line, and then I choose a random point, and then I choose another random line through this point. The probability that I will hit the exact line that I came from is very small. Compared to the probability that I choose a line, and then a plane, and then another random line, here the probability of choosing the same line that I came from is bigger, because there's fewer lines in a plane than there are in the entire space. So there's different backtracking probability, and it's exactly the same issue that we had before. So when we compare the lower and the upper random walk, we should always factor out the higher collision probability that goes into the upper walk. And in fact, if you want to be absolutely careful and kind of, it's not always, the problem is not always in the upper. Sometimes it's actually the problem is in the lower. It depends if your subspaces have dimension that is very high compared to the ambient dimension or very low compared to the ambient dimension. But I shouldn't have even said that. OK, So we have this poset, and now we're just going to make the same definition as before. So here I just wrote lines, planes, blah, blah, blah. Anyway, we can't see it, so it's OK. And the same definition from before is still meaningful. So you can still, this operator is still well-defined, this L plus non-backtracking. And this operator is still well-defined, L minus. Because what is this operator? You just look at this graph with a vertex for every line or plane or object in your poset, and you just look at this random walk. It's still the same thing. It doesn't matter whether this multi-layered graph came from a simplicial complex or not. And you can still ask whether these two operators are similar in spectral norm, and that's going to be our definition for a high-dimensional expander. OK, very good, very good. OK. So we unexpectedly closed. And now, OK, we did this. OK, good. So I guess I have two more slides to go, which is good. So here is something you can do with this with this outlook on this object, which is you can do Fourier analysis like we do on the Boolean hypercube. So you think of having a real-valued function on the d faces. Okay, so you have a function that labels every subset of size d with some real number. And you want to understand this function, decompose it. Why do you want to decompose it with respect to this high-dimensional expander? Well, one reason is that maybe you're interested in a set of d faces, and you want to understand what is the behavior of this set when you do a random walk. How many times do you exit this set? And this is exactly what was a key problem that Dor was talking about. So often we are interested in functions on the d faces. They represent maybe a subset of subsets, and we want to understand these functions. And so it's good to decompose them according to a good basis that respects the geometry that is underlying them. Okay? So here is a nice thing. A function, a real-valued function, can be written as a sum of, OK. So there's a shift here, actually. So d faces are like d plus 1 subsets. So the minus 1 is like the empty set. The 0 is the function on the vertices, and so on. So I apologize for this shift. But this is the notation that's what is conventional for simplicial complexes. So you can write a function on the d faces as a sum of different components. And what are these components? So each fi, the ith component, you really should think about it as if it's a function on the I faces. Okay? It's like you're looking at a function on the d faces, but you can decompose it to a function on the vertices, plus a function on the edges, plus and so on. And you're averaging out? Yeah, something like that. You average out, but you need to be orthogonal to the previous layer. So something like that, some exclusion-inclusion thing. So I want to just say, the way to think of it is that this is analogous. The fi is like analogous to the part of your Boolean function that is Fourier degree I.
What is the dimension?
D is the dimension. So suppose you're looking at simplicial complex of dimension d. Maybe it has dimension more than d, but you're looking at dimension d, and you have a function there. And you have a decomposition like this. Right. So what you're saying is the slice. It's not the hypercube. It's the slice. And what you would get here is exactly the decomposition that Yuval Filmus and Mossel and Guy, all these people worked on. You get the exact same thing. OK, let me finish. This is only an approximate decomposition. It's, OK, so what do you know about this decomposition? So you have the fi. It's the part that corresponds to degree I. These fi's are orthogonal to each other up to this. I'm sorry, but there's a gamma here. OK, so they're almost orthogonal to each other in the sense that the norm of the entire function, the square of the norm of f, is equal to the sum of the squared norms of the pieces up to this gamma. Also, this fi is an approximate eigenfunction of these up-down operators So it's an approximate eigenfunction, and it has an eigenvalue lambda I. So it doesn't, this lambda I depends on the complex. It doesn't depend on, yeah, it depends on I. Okay. What else? Okay, that's it. So now this is the decomposition you can do. And now, Gil, what was your question again?
Okay, so I don't know, with Boolean function on, with the Fourier analysis on Boolean function, usually you think about the range of the degrees is from
0 to n. Right, to n. But here in the slice, but think of the k-slice. So what is the k-slice? In this language, the k-slice is the simplicial complex that contains all possible subsets of size k and below. And then the degree goes only up to k. So it's consistent. So here it says, so this generalizes the decomposition on the k-slice and also on the Grassmann. So you can do Fourier analysis on the Grassmann like Dor mentioned, and you would get the same thing if you do it this way, looking at these up-down operators. This is more general, so, but I would love to see more examples. So, I mean, you can apply it to various posets, but there's a lot of things we don't understand here. For example, when does this decomposition, this almost orthogonality is only true when the thing is really the upper walks and the lower walks coincide. This is what we know how to prove. But maybe this decomposition holds also in other cases that are not high-dimensional expanders. This we don't know. So, yeah, there's a lot we don't know, or at least I don't know. So, and this allows you to import some theorems that we already know how to prove using Fourier analysis and stuff. For example, there's an FKN theorem, Friedgut-Kalai-Naor, that says some structural information about your function if you know that it's only supported on the first Fourier level. But maybe other things are also possible. We don't know. So last slide, the summary slide, right? So how am I doing, Guy? What time is it? Cool. OK, so let's summarize, yeah? So I talked in the beginning about a PCP and how you construct it, and I tried to show how agreement tests play an important role. I showed how it's a component in various PCP constructions that we have. And I view it as there is some kind of geometric infrastructure to a PCP construction. And I believe that really this geometric infrastructure invariably is some kind of high-dimensional expander. So what to do with this analogy, I don't know, but I find it very interesting to study these objects with this perspective, kind of looking at these expanders as the geometry underlying the PCPs. And here's a couple of open questions. This one is kind of, it's not really a concrete question. It just says, look, these high-dimensional expanders look very powerful. The constructions are super non-trivial, and they're very interesting. Can we find more uses for them? So I don't know. And the second question is more concrete, kind of to make us feel like we said something concrete. So I mentioned this before. There is this k-slice. It's the collection of all possible subsets. And there is an object that is sparse. It's bounded degree, and it spectrally approximates this k-slice. And this is the high-dimensional expanders. There's the Ramanujan complexes, and there's other complexes by Tali Kaufman and Izara Oppenheim. So we have a sparse object that kind of simulates the k-slice. What about having a sparse object that simulates the Grassmann complex? So the Grassmann is the same as the complete k-slice in the sense that you take all possible k-dimensional subspaces. And there is work, kind of older work by Ran Raz and Dana Moshkovitz that give some kind of sparsification. They look at some kind of plane versus plane test or line versus line test, but they don't take all the lines. But their sparsification is far from being bounded degree, and I would really love to see a Grassmann complex that is actually bounded degree. So that's the second question, and let me show you this beautiful picture. So we're going to have in the summer this program on high-dimensional expanders and error-correcting codes, and you see this, the graphic designer drew this beautiful picture where you see the complex is above, and there's some infrastructure, and there's the bits of the code, and somehow if we understand the geometry, maybe we can construct better codes. So maybe that will give us some new applications for HDX. I don't know. Okay. Continuations.
This either some specification can help with this problem or it's not?
Actually, okay. I don't know. There's two different interesting things going on in the 2-to-2. One is this very strong overlap, and the other is this covering property. And without getting into details, if you have a sparser object, you can hope for better covering property. For example, Bose has this direction where you, instead of looking at the short code is some kind of generally, you can think of it as some kind of higher degree version of the Grassmann, whatever that is. And I'm getting into too many details. Maybe we take it offline. Okay. Yeah, I mean, okay, just to summarize. So if you have a sparser object, you might have better covering property. Maybe it will lead you somewhere. That's a bit far-fetched. A more concrete application for this is to construct a locally testable code with constant rate, which is a very big open question and seems maybe not within reach, but just after that. So.
After the next two.
After that? So. Okay, yeah.
Yes, so you mentioned the shortcode. How does the shortcode fit into this picture?
Okay, so what is the shortcode? So the shortcode, if you want to encode some k-bits, you look at all possible functions over these k-bits that have degree s. Okay, if the degree s is 2, you get something like the Grassmann. If the degree s is bigger than 2, like s, then you get the shortcode. And now when you want to, and it turns out that this is a really beautiful paper that this shortcode, it's much shorter than the long code, but it still behaves like the long code. So you have a long code test for it, and you have a unique test for it. Okay, so it's good in the sense that if you can use the shortcode, you have a unique test. What is bad about the shortcode? It doesn't have the subcode covering property. And the reason it doesn't have subcode covering property, I don't have energy to, I cannot do it now. But anyway, you can hope that maybe a sparser object will do something. I don't know. Okay, thanks for the question.